Good afternoon. My name is Jesus Labarta. I'm Director of the Computer Science Department at the Barcelona Supercomputing Center and Coordinator of the POP Center of Excellence. And I will be presenting today the 6th of a series of webinars that we are doing about performance analysis and parallel programming. And today I will be focusing on the analysis of sequential computations inside parallel programs. I will go through a small review of the content of a previous webinar about the analysis of the parallel size of the efficiency, to enter then on characterizing the computational efficiencies of the user level code of the sequential computation parts. This is going to be the main section of the presentation, and then I will go into details of how to go to inner levels of detail and analysis to finalize with possible extensions for future webinars. So just reviewing a little bit, the typical way of presenting performance can be through speed up plots, where we show how much faster go with P processors as compared to a reference number of processors. And we plot these speed up curves compared to the ideally linear speed ups, or we can refer this number to the actual increase in the amount of resources and get a normalized value which tells us how efficiently are we using the additional resources. This is a very high level, very coarse level presentation of how our application scales. But if we want to get insight on the internals, on the details on why is the plot like that, we can go to detailed profiling or detailed trace analysis, and this is what we have in our tracing packages. That can allow us to go to very, very deep detail insight, but at the expense of having to handle large data and having to navigate through that data. And the question is, can one get some insight about factors, fundamental factors that describe or explain the behavior of our application, but still are just a few numbers? And this is what was the subject of the previous POP webinar, where we presented that the parallel efficiency can be described as a multiplicative model of load balance, serialization, and transfer. These factors are three numbers that tell us how their evolution with increased core count tell us what are the fundamental limiting aspects of the behavior of the application. We can have, as in this case, we have a very good serialization, no issue with that. We have load balance, which is not perfect, but is still fair. It's 0.9, around 0.9, and is stable, doesn't change much with increased core count. And we have transfer, which is good at the beginning, close to 100, close to 1, but it gets worse with increased core count. So this was one way of looking at the parallel behavior of the application with a simpler model. What we are going to target today is just to state that certainly parallel efficiency, concurrency, having a lot of people working at the same time is important, but it's also really important to make sure that each of them works at a good performance, delivering good performance. So what we are going to try to see is there a kind of equivalent to the previous model that quantifies in a high-level, simple, abstract mode the way our sequential computations are behaving. And then we can dig down into more detailed analysis of why that is happening if we detect a core level problem with some of these metrics. Before that, I will be talking about the basic mechanism on which we rely for doing the analysis of the computation parts in the user level code. And this mechanism is hardware counters. Available on all processors, is typically possible to read a few of them, not a huge number, although the architecture may support large numbers. One has to select some of those, and we typically rely on counters which like number of instructions or cache misses at the different levels of the cache hierarchy or cycles. These are accessible typically through the PAPI interface and can be read by the tracing package. Our tracing package is called extrae, and actually it intercepts all entries and exits of MPI calls or OpenMP calls or hybrid. And so it intercepts entries and exits to the runtime, and at each of these, it reads the hardware counters, which essentially gives you the actual amount of instructions or the actual amount of cycles or cache misses in the interval between the previous exit of an MPI call to the entry of the next one. We also read it at we read at the exit. So if for each of these computation phases, we have information about how many instructions it did, how many cycles it took. And because the events are time-stamped, we also have information about how long was that in terms of elapsed time. The specific hardware counters that are read are controlled by an XML file, which is just activated. The instrumentation mechanism is activated by modifying what would be your typical submission scripts, where you would do an MPI run with a binary and maybe arguments. Is by introducing this small shell script here, where you can specify first which is the configuration file that will determine which hardware counters are read. And second, we'll set up the dynamic interception mechanism for the runtime calls to be intercepted by the instrumentation library. The extract configuration file, XML file, which specifies which hardware counters to read, has one section just about that. Okay, so here you say which are the counters that you want to get captured at every entry and exit of the runtime call. And a typical configuration file is this one, where you instrument, let's say, instructions, cycles, L1, L2, L3 misses, maybe floating point instructions, or maybe branch mispredictions. So these values captured in the trace let you do either derived, basic, or derived metrics. In basic metrics, for example, the instructions was a counter that was already in the available trace. You could compute other metrics like hardware, so cache miss ratios, or the statistics about the architectural behavior. But the ones we are interested in is metrics about the performance, metrics about instructions per cycle, or about frequency. And these metrics I am showing here, they're easy to capture, easy to compute based on the available data on the trace. You have the instructions, you have the cycles, you can compute IPC. Frequency is also interesting because you have the cycles, you have the duration, the elapsed time between the events, and then you can compute the effective frequency. And I want to make a small comment about this because frequency is no longer something really very much under control of a programmer. The good old times are gone. Now the frequency at which a call runs can be selected by governors or power capping mechanisms, or by many different things that can make the actual frequency to be changing a long time, be different between cores. And there is also in another aspect which can also change the result of what we consider this measurement of frequency, which is preemptions, interrupts, operating system noise. If in the typical run you would expect this run to execute this number of instructions and cycles and take this time, if there is an interrupt coming in between, this interrupt, and because of the hardware counters are virtualized, will let time go by. Of course, no way to inhibit that, but will not account the number of instructions and cycles in this interval to the actual read that is done at the end of the period. So what should have taken this amount of time will actually take this amount of time, but will have the same number, or essentially equivalent, similar number of cycles and the same number of instructions. The result is that the effective frequency, as reported by this metric, will be less than what we consider, if that ever happens, and now and in the future, the nominal frequency of the device. And just to let you see a little bit how this can be in real applications today, I have two traces here, and I represent one row for every process. And the color is light green, means that the frequency was low. Dark blue means that the frequency was high. And you see that in systems today, there is very, very dynamic changes across cores a long time of the frequencies. It can be uncorrelated with the actual application behavior or can be correlated. In fact, there is phases where there is low frequency and phases where there is high frequency. So this was a comment about this metric, which we think has to be taken into account. And in reality, if we enter on the core content, which are the efficiency factors that we consider are relevant to describe in a very high level, very abstract level, the computational efficiency of the computational parts in the user level code. And we would like to use three factors, again, three terms. One having to do with how is the computational complexity of the regions scaling. So is the total amount preserved? When you do strong scaling, you would expect the number of instructions, total number of instructions to be the same, irrespective of whether this is done by 2, 4, 8, or 100 processes. So there should be a number that characterizes that. Number essentially between 0 and 1 can be that describes this metric. There's another factor which is important, is how fast is the processor executing those instructions. So it may be that with larger core counts, the IPC gets worse than what you had with lower core count, or it may be that it's better. This may also happen. And the third factor is about this frequency efficiency, which essentially means are we really preserving the frequency when increasing the core counts? And these metrics are easy to compute. These are just ratios taking into account, for example, the number of instructions with a reference core count. They are all relative to the reference, and the number of instructions with P processes. And ideally, you would like this thing to be 1, which would mean that the same number of instructions is executed with P processes than with the reference. But if there is code replication, this number will grow and the efficiency will be less than 1. Something similar can happen with IPC, for example, and if the IPC with P processes is less than the IPC with the reference case, the efficiency will be lower, below 1. It might actually even happen, that's why we put these numbers to be between 0 and 1 ideally, but can be a little bit higher. It might happen that with higher core counts, the IPC gets better. I mean, cache issues might, for example, impact on this. And the other term is frequency efficiency. So for all of these, essentially, the important thing is they are typically related to a reference core count, and they have to be computed for the user level code. So discarding the number of instructions in MPI and discarding the IPC in MPI, which can be very, I mean, maybe a little bit high in some cases, but measuring it is not indicative of how is the user level code behaving. So with this model, we have these three factors that describe what we call the computational efficiency. Typically, ideally, the reasonable case would be a computational efficiency around 1, which we can combine with a parallel efficiency of, again, constituted of 3 factors. This was the previous webinar topic, so load balance, serialization, and transfer. And these 2 numbers can be combined into a global efficiency. And with these 6 numbers, we have an indication of what is the fundamental reason that is controlling or determining or underpinning the observed application performance. This can be computed, in our case, obtaining the traces of different core counts by a single Python script that essentially computes these metrics for the different traces and helps us build this type of tables, which is what we typically report in the POP studies. If I look at one of these tables, for example, here, we see that, well, the global efficiency starts being not very good, and understanding by not very good below 0.6. Okay, the coloring scheme is here, but everything which is blue is understanding is relatively fine, relatively okay. Everything below, the darker or the reddish the color is, the worse the situation is. So we see here a situation where there are 2 factors. One of them is computational efficiency, which is 0.84. Actually, is not each of the individual components. This is what we have been seeing, the IPC, instruction, or frequency. Each of them is not that bad. It's okay, but the product of them gives something like losing kind of 16% efficiency losses. We have, nevertheless, on the other side, a transfer efficiency factor, which is even a little bit worse. This transfer efficiency factor results, combined with the load balance and serialization, results in this parallel efficiency. And this parallel efficiency, combined with this computational efficiency, result in this global efficiency. What we have here is that in this case, which is a kind of balanced type of interaction impact between transfer and computational efficiency, at least for these core counts, you can have other applications where computational efficiency is the real bottleneck. And in this case, this was in a case where the problem was mostly due to IPC scalability, while the parallel efficiency was okay. Actually, the number of cores was low. You have other cases where the problem is the parallel efficiency. And even if the computational efficiency starts being a little bit limiting also, in this case, the parallel efficiency was worse. What I'm trying to say is that for every application, what we think is the important thing is that we should be able to get these numbers with minimum cost. These numbers give us a kind of a global language where to express and to compare even between applications and to understand the fundamental reasons of the fundamental directions of what to address. So it's really not very interesting to work on this application on overlapping communication and computation. What we have to work is on improving the IPC. So these numbers give us the kind of insight and direction of where to go with the optimizations. So this is the first content of the basic component of the webinar. And what I will go down now is, well, but in the consideration, those numbers are global, are nice, but they present a very, very global structure of the application. Can we get to thinner levels of understanding? And here the presentation is the techniques that we're using is a clustering technique. And essentially the approach is we can have a timeline with for every process, we have a metric painted as a grading here between green, light green, which is low value of the metric, and dark blue, which is a high value of the metric. And this metric can be, for example, how many instructions are completed in the interval. There can be another metric, which is the IPC, instructions per cycle. But here we have the dimension of space, processes, and time. Can we get rid of these dimensions and project that into a two-dimensional space where we get rid of space and time, and we only represent for each of these points how many instructions it executes, and for each of them how much IPC it gets? And this is a scatter plot where all that data is captured, which shows some structure, and this structure can be actually detected automatically by a clustering algorithm. In our case, we use a density-based clustering, and it can be fed back into the timeline, and we can see the structural behavior of the application along time and along processes, and we see that this is typical to have the situation of kind of bolt synchronous application, everybody doing the same type of computation at a given point in time, and then shifting, going to the next one and to the next one. And we have this level of description here where we have a good description of the computational structure of the regions. An interesting one, for example, is this one, which shows imbalance because significant difference in number of instructions, but also shows imbalance in IPC. And actually, the regions, there are some of these samples which have more instructions and less IPC, and others have less instructions and more IPC. So this actually means more IPC, more imbalance than what one would consider only by looking at instructions. And this actually raises some potential interesting things or questions. Is it would be nice, can we improve, for example, the IPC for all of these regions to have the same one? Or can we achieve a better load balance for this region, which actually does not happen on the others? The others are more spherical on this case. So this is a first technique, which we consider very important. There's another technique is you can do that analysis of clustering and detecting the different regions for a run of 64 processes, for a run of 128, or for a run of 192. The question is this, because these are 3 or 6, in this case, independent clustering analysis, we don't have a clear what's the correspondence between each of them. So the techniques that we're using here is tracking techniques in the same way that you track human persons in a scene. For example, the movement, you can track the movement of these points in this two-dimensional space. and really identify which of these clusters in one of the frames corresponds to the same region of code in the other frame, and detect essentially how each of these regions move. This is how the centroids of those regions move when you increase, for example, core count. And we have here an example where this is a typical something expected. So more cores, less instructions per core. So this is expected. IPC does not change, so this is also reasonable. We have a case here where increasing core count improves a little bit IPC. We have some cases, interesting cases here, where actually increasing core counts at the level of the parallel run does not reduce the size, this amount of instructions executed by the program in some of the regions, and this is a potential scaling problem. Okay, this is replicating code, and this is so we detect an issue far beyond these things can become a real problem. So these are the two basic techniques that we have been will be now showing some examples. If we wanted to do further, deeper analysis, what would be the next step? Okay, so what we have presented till now is a simple model, is an abstract model that can provide global description of things. But if we want to go to further details, the issue is that these metrics in reality depend from many inner deep architectural characteristics or deep operating system aspects or algorithmic instruction mixes. So the detail, the search space starts being fuzzy. One can, in this fuzzy search space, really go dig down by looking at the timelines where you can present timelines that describe all metrics derived from the hardware counters, like IPC frequency that we have presented, but you can also look at level 1 misses per 1,000 instructions or level 2 or level 3. Even if looking at the traces you can go into very deep details, we wouldn't recommend this, as we still think there should be a kind of a progressive top-down approach, and still probably a next level is what I'll be discussing, which is do the tracking analysis, but not only for the instructions and cycles and IPC metric that we have presented, but try to do analysis for more derived metrics. So it's essentially applying the technique that I have presented about tracking to, for example, this is an MPI run with different number of processes. We see how this reduces the execution time, how the structure detected by the tracking kind of is more or less the same at the different core counts, and we can see how, when increasing core count, these points, this shift or move in this space of instructions and IPC. And we see, for example, there are some regions, they all go down because it's a strong scaling. We see some regions that at some point start getting a little bit lower IPCs. In order to gain more in depth of this, we can do the same plots and just represent different metrics in different projections of the same tracking. This is the original one in instructions and IPC, but while we can, for example, keep in instructions, we can display the evolution of misses per second, misses per instruction at level 1, at level 2, or level 3, or even the ratios between how many L1 misses per L2, every L2 miss, or how many L2 misses per every L3 miss. And with these plots, one can analyze, for example, typical very global things is yellow region has poor IPC. It's clear that it has high misses per 1,000 instructions, 80 misses per 1,000 instructions, has a high L2 misses and has high L3 misses. We can see that, for example, for many, by looking at the ratio between L1 and L2 misses, that many of these regions have, well, not even 2 L1 misses per L2 miss. Okay, there's one of them which is close. So the number of L2 misses per L1 miss is not very high. And we actually see that there is really not much change for this execution, not much change, except in some situations of the shapes of these metrics. So the idea is this is a mechanism to have access to a wide range of metrics and how they evolve with increasing core counts. And this is where the analyst can start looking at the potential reasons of the problems. In this case, there is not much change with the core count. I can present another example where what you see, for example, is a region which gets an IPC which was significantly worse as core count increases, while other regions have the similar to the previous case, some variability, but not that large. Also, other regions have these strange behaviors that suddenly change the behavior of the application. So you can do the same thing, and you can actually look at, for example, I'll be looking only at what's going on with this green region, which gets significantly worse IPC when you increase the core count. And if we look at the L1 misses, we see that the L1 miss rate actually increases with increased core count. The L2 miss also increases with increased core count. And the L3 miss does not increase with increased core count. Okay. From these plots, one can make hypotheses about what's the fundamental reason of the bottleneck. In this case, is a topic related. This increase of L1 misses is something that the speculation may be, well, this is an MPI plus OpenMP. This may be related to the fault sharing effects, and then one would have to, having a hypothesis, one would have to find out whether with the available hardware counters this is a hypothesis that can be validated, or we need additional hardware counters. The comment is that one can track the evolution of this in this space when increasing core count, but there are many other changes that can be tracked. For example, what happens if we increase problem size, or we had an example here of what happens if we change compilers or we change machine for the same code. And we had the tracking here that some of these changes correspond to a change in compiler, some of them to a change in machine. And you can really look at compare the behavior of the same code on different machines, not at the very coarse, gross aggregated level, but by looking at the internal evolution of some of the individual regions in the program. So what I have described is the basic techniques. What would be additional techniques for more in-depth potential analysis is other techniques available to compute all hardware counters from a single run of the program. And what we saw before, we had a set of maybe 8 hardware counters, and we could compute all the metrics with these 8 hardware counters, but we could not use, I don't know, 20 or 40 or 50 hardware counters that we may want to do if we want to proper characterization of the instruction mix, proper characterization of all the levels of miss ratio, or proper characterization of the stall causes. So we have techniques for doing this, and we have techniques for doing fine-grained analysis. What we saw today, each of these regions can be between MPI call and MPI call, can be a few tens of microseconds, milliseconds, a few tens of milliseconds. Internally, the behavior, which was described by just 2 numbers, instructions and cycles, or IPC, it really internally it can change a long time. So the idea is, can we have tools or techniques to get the instantaneous evolution of those metrics inside these computational regions? And describing this thing is another topic of further detail that can be left for a further webinar. So with this, I finalize the description of the current webinar. The idea is you have learning material in the POP web page. This type of analysis are things that we can perform for different people, or we can help, or we can train how to go into the details for people to do those themselves. These are part of the activities of the POP Center of Excellence. And if you were interested in using them about them, or getting more insight about them, you can apply on the POP website. The POP project is a Center of Excellence funded by the European Commission. The funding is finishing now, but we have very successful experience, and the partners are continuing the activity or attending or servicing this website. With this, I finalize the webinar presentation, and I'm open to questions that may be made. You have on your go to access page, you have the possibility of making questions, and I would be happy to answer if there are questions about the presentation. I have one question here, which is, how easy is it to relate the clusters to the source code? In reality, the information which is captured at the entry and exit of MPI calls includes a call stack at that point at the entry, a call stack at the entry of the MPI calls. So by having this call stack, you can really identify where in your program and which specific MPI call from which specific MPI line is user level code line is doing the MPI call. You can do that for the call at the beginning and for the call at the end, and this kind of focuses on lets you identify the region. In the sample case that I give as future extension, you can do that microscopically at the level as the program for each of these very, very fine grain measurements. In reality, also in that information, which is the syntactical structure of the application, is actually used as one of the heuristics in the clustering, in the tracking algorithms. Okay, I have another question, which is there any option to link performance to a power consumption? Sure. I mean, I've been talking about hardware counters, which have to do with the performance of the application, but you can also read even through PAPI, or you can also read hardware counters related to the power consumed by the application, and you can do the same type of analysis that we presented with those, especially the region, what I've not, one of these things for future webinars, which is about the instantaneous evolution of the power consumption. That's possible. About this thing of the power, the typical situation is that many of the measurement systems are relatively coarse grain. So you can measure power every certain number of milliseconds. And what we can do is kind of really give metrics at much finer granularity, estimate values at much finer granularity. I don't know if there are other questions. I don't see any other question now. If there is no other question, I would close the webinar, just insisting, recalling you the possibility. I've been presenting the technique. The technique is, I think, is really powerful. But if you are interested on trying it, or on us giving you guidance during the first analysis on some application, please tell us through these contact links, and we'll be more than happy to discuss specific needs or specific use cases. With this, thank you very much for attending the webinar, and if you are interested, we can see you in future webinars organized by the POP Center of Excellence. Thank you very much.